In our past experience of oxidation reduction, one of the chemicals that was often used was potassium permanganate, which is a purple chemical that then decolorized when we reacted with things like iron 2 sulfate, hydrogen peroxide, things like that. What we've just seen in a quick demo is that there's actually some other possible things that can happen depending on whether you acidify the solution first or not. So it actually has three different reactions, whether you're working under acidic conditions, neutral conditions, or alkaline conditions. And we need to know how to balance half equations for all three. So in our first reaction that we looked at, we had purple permanganate turning into a colourless solution, which we know is manganese 2 or Mn2+. So we can use those observations to write the start of our half equation. And this is the one that we met last year, so most of us have actually learned it off by heart rather than learning how to balance it. Shortly I'm going to go through how to balance it though, just because that's important. Okay. Under neutral conditions, so when I put it with just water, we actually noticed that it went from purple to a brown solid. So we've got permanganate, MnO4-, and we just need to know that that brown solid is MnO2. So it's a new one for us to learn, manganese 4 oxide or manganese dioxide. By coincidence, it's also the catalyst for hydrogen peroxide auto-oxidizing. So hydrogen peroxide reacting with itself to make oxygen and H2O. All right? By coincidence, it's not because. And the alkaline one was probably the coolest one because we didn't expect this. It went from purple to green. It also made some of the brown solid because clearly it wasn't that alkaline the solution we used, but it went from purple to green. So again, the purple is permanganate, and we need to know that the green is called manganate. So take per off the start, basically, which is MnO4-2-. So it's manganese 6 rather than manganese 7. I'm going to go this one first, because it's the easiest, then this one, because it's the hardest, to show you how to do it. In this one here, you can see that all of the atoms are balanced. 1 manganese on each side, 4 oxygens on each side, but what's not balanced is the charge. We also should know that this is a reduction reaction because permanganate is a strong oxidant. It causes other things to be oxidized, so it's easy to reduce. So all we need to do is balance out those charges with 1 electron there. Makes this a very easy one to use for balancing whole equations, because depending on the number of electrons in the oxidation half equation, depends how many times I need that reaction to be multiplied. Okay, so it's a nice easy one. The top one's also quite easy because we've met it before. But because of that, I want to go through the process. The manganese may be balanced, but the oxygen is not. So I balance the oxygen using water, because water is neutral, so it's not going to affect anything about this. So there's 4 oxygens, therefore there's 4 water molecules being produced. By putting water in, I introduce hydrogen ions to this. Must be hydrogen ions because the H cannot be undergoing oxidation or reduction, because that would be introducing something new. So it has to be H+. And here, hydrogen has an oxidation state of 1. It must also have an oxidation state of 1 over here. It can't be involved in redox, just for balancing the equation. So 4 times 2 is 8. 8 H pluses. The net charge on the left-hand side is now -1 plus 8 times 1, so it's positive 7. The net charge over here is positive 2. The difference between 7 and 2 is 5, so that's how many electrons must be being transferred. So I add 5 electrons to this side, so that the net charge on both sides is now positive 2. And that's my general process for balancing any equation where there's things like oxygens and hydrogens that need to be balanced. When it comes to neutral conditions, it gets a little bit trickier because we can't have hydrogens over here because we just said it's not acidic conditions. We can't have them. So what molecule or ion should be on this side if it's neutral? We'd expect it to be water. We'd expect it to be water because that's our neutral molecule. If it's alkaline, by the way, and we have to go through the same process, we'd expect OH to be on this side. It's not required in this one, but if you had to balance one, you'd put OHs on this side. It's actually really hard to do, so I'm going to show you the process. The process is the same as this, and then you do a next step. So, the oxygens aren't balanced, so I'm going to put 2 waters over here. I know this is wrong, because the waters have to be over here, but just bear with me on that. I know it's wrong, because that gives me 4 H pluses. Okay, that gives me 4 H pluses, that's a problem. Okay? Then that gives me a net charge of 0, net charge of 3, so I need 3 electrons. I'm not quite finished. I have to get rid of those 4H pluses. So this is a bit like Hess's law, where we're going to use another equation to get rid of something that doesn't belong. And what doesn't belong is the H plus. Luckily, we know of a nice equilibrium, so I can go either way. That means I can write it either way around. I want to get rid of them, so I need to cancel them out. And this equilibrium is that, the water dissociation equilibrium. This has got hydrogens on both sides now. So I can multiply this by 4 to cancel those out. So I go 4 of those, 4 of those, and 4 of those. And what that does, quite conveniently, is gets rid of those. But at the same time, it also got rid of those, didn't it? And rather than 4, this becomes a 2. All right? Because 4 minus the 2 on that side is 2. So the process was the same as here, and then we used something really similar to Hess's law to get rid of something that doesn't belong. Conveniently, look what else it also introduced for neutral conditions. H2O as a reagent, which is exactly what we'd expect to see. So our final equation here would be MnO4 minus plus 2 H2Os plus 3 electrons goes to MnO2 plus 4 OH minuses. Do a double check. The net charge on this side is -4, -1 there and -3 there. The net charge here now is -4 due to those. If the charges are balanced, you know you've got it right. So, something like permanganate can undergo reactions under 3 different conditions. Okay, you need to know how to balance it under acidic, because that's the basis of all balancing half equations. Then you need to know to use the dissociation of water to get rid of the hydrogens as a product, as a reagent for neutral and alkaline conditions, and that will end up giving you the right answer. Remember, in alkaline, you'd expect OH to be one of your reagents if it needs those atoms to be added to the product, to make the product. Any questions on that before I turn this off? Yep.
With the neutral reaction,
yep.
because it produces OH minuses, wouldn't that therefore make it alkaline as it goes through the reaction?
Yes, it does. So if I carry that reaction on, you'll see it make the brown, and then it'll start making the green. Okay, and I'll try and find, there's a video of this really good one on YouTube that I've found that I gave to my class last year that I'll try and embed into the blog this year as well. It is very good and shows exactly what you just asked, that it does, it goes from brown to green. Yeah, good question. Any others?